You're sitting at a device right now, listening to these words. Maybe it's a phone that fits in your palm, more powerful than the computers that sent humans to the moon. Maybe it's a laptop, casually performing billions of calculations per second while you barely notice. Or perhaps it's a tablet, a device that would have seemed like pure magic to someone just a few decades ago. We take these machines so completely for granted that we forget how impossibly strange they would seem to our ancestors. These boxes of lightning and logic that have become extensions of our minds. Welcome back to Midnight Deep Dive. If you're new here, welcome to a cozy corner of the internet where we explore fascinating stories that shaped our world. I'm so glad you've decided to join me tonight, wherever you are, whatever brought you here. Tonight, we're embarking on a journey through one of humanity's most remarkable achievements, the evolution of computers. This is a story that spans thousands of years and touches on mathematics, warfare, business, creativity, and human connection. It's about people who dreamed of machines that could think, inventors who worked in garages and laboratories, and the gradual realization that we were creating something that would fundamentally change what it means to be human. So find your coziest spot, let the day's tensions melt away, and drift with me through a story that spans from ancient merchants moving beads on strings to the smartphones we unconsciously reach for dozens of times each day. Close your eyes and imagine you're a merchant in ancient Babylon around 2400 BCE. You're sitting cross-legged in your stall at the marketplace, surrounded by clay tablets inscribed with cuneiform, jars of grain, bolts of cloth. A customer wants to purchase several items, and you need to calculate the total cost. You reach for your most valuable tool. Not a pen, not a ledger, but a simple frame holding rows of beads threaded on wires. This is the abacus, and it's humanity's first computer. The word computer originally didn't mean a machine at all. For most of human history, a computer was a person. Someone whose job was to compute, to calculate, to work through mathematical problems with pen and paper. But the desire to mechanize calculation, to find tools that could help us count and figure, goes back as far as civilization itself. We're pattern-seeking creatures who needed to track harvests, predict seasons, manage trade, and measure land. Mathematics wasn't an abstract exercise. It was survival. The abacus appeared independently in multiple ancient civilizations. The Mesopotamians had counting boards. The ancient Greeks and Romans used the abacus for calculations. In China, the suanpan emerged around the 2nd century BCE, while Japan developed the saraban. These weren't primitive toys. They were sophisticated calculating instruments that, in skilled hands, could perform complex arithmetic with remarkable speed. Merchants could multiply large numbers, calculate percentages, even work out square roots using systematic techniques passed down through generations. What makes the abacus fascinating from a computing perspective is that it's a physical representation of an abstract system. Each bead represents a value, each rod represents a place value, and the position of the beads encodes information. Move the beads according to certain rules, and you're performing calculations. You're processing information through a mechanical system. This is the conceptual foundation of all computing, taking abstract ideas and making them concrete, creating physical systems that manipulate symbols according to rules. For thousands of years, the abacus and similar tools represented the peak of calculating technology. But humans kept dreaming bigger. What if we could build more complex machines? What if we could automate not just simple arithmetic, but more sophisticated calculations? The first significant step toward mechanical calculation came in the 17th century, when European thinkers began designing devices that used gears and wheels to perform arithmetic. In 1642, a 19-year-old French mathematician named Blaise Pascal created what's often considered the first mechanical calculator. Pascal's father was a tax collector, and young Blaise, watching his father struggle through endless tedious calculations, decided to build a machine to help. The Pascaline, as it came to be called, was an elegant brass box containing a series of connected gears. You'd enter numbers using dials, turn a crank, and the machine would add or subtract, with the gears automatically handling carries between digits. The Pascaline was a marvel of mechanical engineering, but it was expensive, difficult to build, and not particularly practical for most purposes. Only about 20 were ever made, but it proved a concept. Mathematics could be mechanized. Calculations could be automated through clever mechanical design. This wasn't just a labor-saving device. It was a philosophical statement about the nature of thought and mathematics. A few decades later, German polymath Gottfried Wilhelm Leibniz improved on Pascal's design, creating the stepped reckoner around 1672. Leibniz's machine could not only add and subtract, but also multiply, divide, and even extract square roots. He used a clever mechanism called the Leibniz wheel, a cylinder with teeth of increasing lengths that would engage with gears in different ways, depending on how far you rotated it. This design would influence calculator construction for the next 3 centuries. But here's what's remarkable. Leibniz understood that his machine was doing more than just arithmetic. He developed binary mathematics, the system of ones and zeros that would eventually become the language of all digital computers. Leibniz recognized that you could represent any number using just 2 symbols, and he even speculated that mechanical systems using binary might be simpler and more reliable than decimal systems. He was right, but it would take nearly 300 years before his insight would be fully realized in electronic computers. Throughout the 18th and early 19th centuries, mechanical calculators gradually improved. The Industrial Revolution brought better manufacturing techniques and more precise metalworking. Businesses increasingly needed to perform calculations. Insurance companies calculating premiums, banks computing interest, governments managing taxes. The demand for calculation was growing, and with it, the dream of truly powerful calculating machines. Enter Charles Babbage, a brilliant and somewhat cantankerous English mathematician and inventor. In 1822, Babbage proposed his difference engine, a machine that would mechanically calculate mathematical tables. At the time, printed mathematical tables, logarithms, trigonometric functions, navigational calculations, were essential tools for scientists, engineers, and navigators. But these tables were created by human computers who calculated values by hand, and they were riddled with errors. A single mistake in a logarithm table could cause a ship to navigate incorrectly, potentially leading to disaster. Babbage's vision was to eliminate human error by mechanizing the calculation and printing of these tables. His difference engine would use the method of finite differences, a mathematical technique that reduces complex calculations to repeated addition, something a machine could do reliably. The British government, recognizing the value of accurate tables for navigation and science, funded Babbage's work. But the difference engine was never completed during Babbage's lifetime. The precision required for its thousands of intricate parts exceeded Victorian manufacturing capabilities. Babbage was a perfectionist who kept redesigning components. The project ballooned in cost and complexity. After years of work and considerable expense, the government withdrew funding. Babbage was bitterly disappointed, but he'd already moved on to an even more ambitious idea. In 1837, Babbage began designing what he called the analytical engine. And with this machine, he made a conceptual leap that wouldn't be fully appreciated for over a century. The analytical engine wasn't just a calculator. It was a programmable computer. It would use punched cards, borrowed from the Jacquard loom used in textile manufacturing, to input instructions and data. It would have a store for holding numbers, what we'd now call memory, and a mill for performing operations, equivalent to a processor. Most remarkably, it could make decisions based on its own calculations, branching to different instructions depending on intermediate results. The analytical engine, had it been built, would have been a general-purpose computer. Unlike the difference engine, which could only calculate tables, the analytical engine could theoretically perform any calculation that could be expressed as an algorithm. Babbage had invented the computer in concept, even though the technology to build it didn't exist. And here's where we meet one of computing's most fascinating figures, Ada Lovelace, daughter of the poet Lord Byron and a gifted mathematician in her own right. Lovelace understood Babbage's analytical engine better than almost anyone, perhaps even better than Babbage himself. In 1843, she published extensive notes on the machine, including what's now recognized as the first computer program, a detailed algorithm for calculating Bernoulli numbers using the analytical engine. But Lovelace saw something even more profound. She recognized that such a machine could manipulate any kind of symbolic information, not just numbers. In her notes, she wrote that the analytical engine might act upon other things besides number, and could potentially create music or art if the fundamental relations of pitched sounds could be represented in a form the machine could process. She was describing, in 1843, the fundamental insight that would lead to modern computers' ability to process text, images, sound, and video. The idea that anything that can be represented symbolically can be computed. Sadly, neither Babbage's difference engine nor his analytical engine were built during the 19th century. Babbage died in 1871, his grandest visions unrealized. Ada Lovelace died even younger, in 1852, at just 36 years old. Their ideas were too far ahead of their time, the technology insufficient for their ambitions. But their conceptual work laid foundations that would be rediscovered and built upon in the 20th century. Meanwhile, the practical world of calculation continued. Throughout the late 19th century, the need for data processing exploded. Governments conducted censuses that required tabulating millions of records. Businesses needed to track inventory, process payroll, analyze sales. The answer came from an American inventor named Herman Hollerith, who developed electric tabulating machines using punched cards. Hollerith's machines were used to process the 1890 U.S. Census, reducing the tabulation time from 8 years for the 1880 census, done manually, to just 1 year. His punched card system, where holes in specific positions on cards represented data, became the standard for data processing for decades. Hollerith's company would eventually merge with others to form IBM, which would dominate the computing industry for much of the 20th century. By the early 20th century, mechanical calculators had become essential business tools. Companies like Burroughs, Monroe, and Marchant produced desktop calculating machines that could add, subtract, multiply, and divide. These machines, with their satisfying mechanical clunks and whirs, filled office spaces. The people who operated them, often women, were called computers. Their job was to compute, to work through calculations that businesses needed. This was the state of computing on the eve of World War II. Mechanical calculators for arithmetic, punched card tabulators for data processing, and rooms full of human computers for complex mathematical work. The electronic computer, the device that would change everything, hadn't been invented yet. But the war was about to create the urgent need and the massive funding that would make it possible. The age of electronic thinking was about to dawn. The year is 1943, and in a basement at the University of Pennsylvania, something extraordinary is being built. It's a monster of a machine filling an entire room containing 17,468 vacuum tubes, 7,200 crystal diodes, 1,500 relays, 70,000 resistors, and 10,000 capacitors. It weighs 30 tons, consumes 150 kilowatts of power, and when it's finally switched on, it will be able to perform calculations at speeds that would have seemed magical to previous generations. This is ENIAC, the electronic numerical integrator and computer. and it represents the birth of electronic computing. But let's back up a bit, because the story of how we got to ENIAC is fascinating and involves one of history's most brilliant minds working under terrible circumstances during the darkest period of the 20th century. Alan Turing was a young British mathematician who, in 1936, published a paper that would become one of the most important documents in the history of computing. The paper, with the rather intimidating title on computable numbers, with an application to the Entschädigungsproblem, addressed a fundamental question in mathematics. Are there problems that cannot be solved by following a set of rules? To explore this question, Turing described a hypothetical machine, now called a Turing machine, that could manipulate symbols on a strip of tape according to a table of rules. This imaginary device could, in theory, perform any calculation that could be described as an algorithm. Turing proved that there were indeed some problems that no Turing machine could solve, answering the mathematical question he'd set out to address. But in doing so, he'd created something more important, a theoretical foundation for computing itself. The Turing machine was an abstract concept, never meant to be actually built. But it established crucial ideas, that computation could be precisely defined, that a single machine designed for general purposes could theoretically perform any computation, and that some problems were inherently unsolvable. These insights would shape computer science for decades to come. When World War II began, Turing's mathematical genius was recruited for a different purpose: breaking German codes. He joined the secret code-breaking operation at Bletchley Park, where Britain's best minds were working desperately to decrypt German military communications. The Germans used machines called Enigma to encode their messages, and cracking Enigma was essential to the Allied war effort. Turing and his colleagues developed techniques and eventually machines to break Enigma codes. The bomb, an electromechanical device, could rapidly test possible Enigma settings. Later, Turing worked on breaking an even more sophisticated German cipher system called Tunny, which led to the development of Colossus, one of the world's first electronic computers. Colossus, designed by engineer Tommy Flowers and operational by 1944, used 1,500 vacuum tubes to perform high-speed logical operations. It wasn't a general-purpose computer. It was built specifically for code breaking. But it demonstrated that electronic components could perform complex calculations much faster than mechanical or electromechanical systems. The existence of Colossus remained secret until the 1970s, so its influence on later computer development was limited, but it proved that electronic computing was feasible. Meanwhile, across the Atlantic, the U.S. Army had its own calculating problems. Artillery firing tables, charts that told gunners how to aim cannons at different distances and elevations, required enormous amounts of calculation. Each table entry required numerous computations accounting for factors like air resistance, gravity, and the characteristics of specific weapons and ammunition. Human computers at the Ballistic Research Laboratory were working through these calculations, but the war required tables for new weapons faster than humans could compute them. In 1943, physicist John Mauchly and engineer J. Presper Eckert proposed building an electronic machine to compute these tables. The Army, desperate for faster calculations, funded the project, and work began on ENIAC. ENIAC was revolutionary in its use of electronic components. Previous calculating machines used mechanical parts or electromechanical relays, which were relatively slow. Vacuum tubes could switch states thousands of times faster. ENIAC could perform 5,000 additions per second, making it about 1,000 times faster than electromechanical calculators. For the first time, a machine could compute faster than humans could manually operate a mechanical calculator. But building ENIAC was an immense engineering challenge. Vacuum tubes were unreliable, they burned out frequently. With nearly 18,000 tubes, something was always failing. The machine generated tremendous heat, requiring elaborate cooling systems. Programming it was a nightmare. You had to physically reconfigure the machine by plugging and unplugging cables and setting switches, a process that could take days for complex problems. And here's a detail that was forgotten for decades. The people who programmed ENIAC were women. 6 female mathematicians, Kay McNulty, Betty Jennings, Betty Snyder, Marlon Westkoff, Fran Bilas, and Ruth Lichterman, figured out how to make this enormous, complex machine actually compute. They worked from circuit diagrams to understand the machine's logic, then devised ways to translate mathematical problems into ENIAC's configuration of cables and switches. These women were incredibly skilled, yet for years they weren't recognized as programmers at all. In the early days of computing, the hardware was considered the important part, the real achievement. Programming was seen as clerical work, less significant than engineering the machines. So when ENIAC was demonstrated to the public and press in 1946, the focus was on the male engineers who built it, while the women who made it compute were often not even mentioned. It's a pattern that would repeat throughout early computing history. Women doing essential programming and mathematical work, while men received the credit and recognition. The revelation of ENIAC in 1946 caused a sensation. Here was a machine that could calculate trajectories in seconds, problems that would take humans days. Newspapers called it a giant brain. The public imagination was captured by this room-sized electronic thinking machine. The age of electronic computers had officially begun. But ENIAC had limitations. It was essentially a very fast electronic calculator, not a true stored program computer. To solve a different problem, you had to physically rewire it. This limitation was addressed by the next generation of machines, inspired by ideas from a remarkable polymath named John von Neumann. Von Neumann, a Hungarian-American mathematician, became involved with the ENIAC project and began thinking about computer architecture. In 1945, he wrote a document describing the design for a new machine, EDVAC, Electronic Discrete Variable Automatic Computer, which would store its programs in memory alongside data. This might seem like a subtle change, but it was revolutionary. In a stored program computer, instructions are just data. You can modify them, manipulate them, and most importantly, you don't have to rewire the machine to solve a different problem. You just load a different program into memory. This architecture, with separate memory for data and programs, a central processing unit that executes instructions, and input/output systems, became known as the von Neumann architecture, and it's still the basic design of most computers today. The late 1940s and early 1950s saw an explosion of computer development. ENIAC, completed in 1951, was the first commercial computer produced in quantity. It gained fame by correctly predicting Eisenhower's landslide victory in the 1952 presidential election based on early returns, though CBS initially didn't believe the prediction and didn't broadcast it until later. IBM, initially skeptical about the computer market, entered the field and would soon dominate it. These early computers filled rooms, required specialized environments with air conditioning and stable power, and were extraordinarily expensive. Only governments, major universities, and large corporations could afford them. The idea that ordinary people might someday own computers would have seemed absurd. But these machines were proving invaluable for complex calculations. Whether prediction, weapons design, business data processing, scientific research. The technology was evolving rapidly too. Those unreliable vacuum tubes were gradually being improved. Programmers were developing better ways to write instructions for computers, moving from raw machine code to assembly language, and then to higher-level programming languages. Fortran, developed at IBM in the mid-1950s, was the first widely used high-level programming language. designed for scientific and engineering calculations. COBOL, designed for business applications, followed soon after. But vacuum tubes remained a fundamental limitation. They were large, consumed lots of power, generated heat, and failed frequently. A computer with thousands of tubes needed constant maintenance. What was needed was something smaller, more reliable, more efficient. That breakthrough was coming, and it would emerge from one of the most important inventions of the 20th century, the transistor. On December 16, 1947, at Bell Telephone Laboratories in Murray Hill, New Jersey, 3 physicists were working on a problem that would change the world. William Shockley, John Bardeen, and Walter Brattain were trying to create a solid-state alternative to the vacuum tube, a device that could amplify electrical signals or act as a switch, but without the tube's disadvantages of size, power consumption, and fragility. The breakthrough came almost accidentally. Bardeen and Brattain, working with a small piece of germanium semiconductor material and some gold contacts, created a device that could amplify an electrical signal. It was crude, but it worked. They'd invented the transistor, a device that would eventually replace vacuum tubes and make possible everything from portable radios to smartphones. To understand why this mattered so much, we need to understand what transistors do. At their most basic, transistors are switches that can be controlled by electricity. A small electrical signal at one terminal can control a much larger current flowing through the device. This means you can use transistors to amplify signals or to perform logical operations, the fundamental building blocks of computing. Transistors could do everything vacuum tubes could do, but they were smaller, used less power, generated less heat, were more reliable, and were potentially much cheaper to manufacture. When Bell Labs announced the transistor in 1948, people recognized its significance for things like hearing aids and portable radios. But the full implications for computing took time to realize. The first transistorized computer, TRADIC, was built for the U.S. Air Force in 1954. It used 800 transistors and demonstrated that transistorized computers were viable. But early transistors were expensive and not particularly reliable. It would take another innovation to really unlock their potential, the integrated circuit. In 1958, working independently, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor both developed ways to create multiple transistors on a single piece of semiconductor material. Instead of manufacturing individual transistors and wiring them together, you could fabricate entire circuits. Transistors, resistors, capacitors, all interconnected, on one chip of silicon. This was the integrated circuit, or microchip. The advantages were enormous. Integrated circuits were smaller, more reliable, fewer connections that could fail, faster, shorter distances for signals to travel, and cheaper to manufacture once the initial production setup was established. The space program became an early major customer. When every ounce mattered for rockets, the small size and light weight of integrated circuits was worth their high initial cost. The Apollo guidance computer, which helped navigate missions to the moon, used integrated circuits. But it was Gordon Moore, one of the founders of Intel, who articulated what was happening in a way that would define the industry for decades. In 1965, Moore observed that the number of transistors that could be placed on an integrated circuit had been doubling approximately every year, and he predicted this trend would continue. Later refined to doubling about every 2 years, this observation became known as Moore's Law. Moore's Law wasn't a law of nature. It was an observation about the economics and engineering of semiconductor manufacturing. But it became a self-fulfilling prophecy. The industry used it as a roadmap, continually pushing to fit more transistors on chips, knowing that if they could double density every couple of years, they'd stay competitive. And remarkably, Moore's Law held true for decades. driving exponential improvements in computing power. Think about what exponential growth means. If something doubles every 2 years, it increases by a factor of 1,000 in 20 years. In 40 years, by a factor of 1,000,000. This is why the smartphone in your pocket is millions of times more powerful than the room-sized computers of the 1960s. This is why we casually carry around devices that would have seemed like magic to previous generations. The manufacturing process for integrated circuits, particularly after the industry standardized on silicon as the semiconductor material, became increasingly sophisticated. Silicon Valley, a region south of San Francisco that became the center of the semiconductor industry, developed specialized expertise in growing pure silicon crystals, slicing them into wafers, using photolithography to create intricate circuit patterns, and precisely controlling the doping and layering processes that created transistors. The level of precision required was extraordinary. Modern chip manufacturing works at nanometer scales, billionths of a meter, distances so small that quantum mechanical effects start to matter. A human hair is about 80,000 nanometers wide. Transistors in modern processors are measured in single-digit nanometers. Creating billions of these tiny structures on a chip, all working correctly, represents one of humanity's most impressive technical achievements. But in the late 1960s and early 1970s, integrated circuits were still primarily used in specialized applications. Aerospace, military, and expensive business computers from companies like IBM. The transistor and the integrated circuit had made computers smaller and more powerful, but they were still costly, complex machines operated by trained specialists. The idea that computers might become consumer products, items that regular people would own, seemed unlikely. Several things needed to happen for personal computing to become reality. First, computers needed to become dramatically cheaper. Second, they needed to become simpler to use. Third, someone needed to imagine why ordinary people would want them. These changes were coming, driven by a combination of technological advancement, cultural shifts, and the vision of people who saw computers not as calculating machines for businesses, but as tools for human creativity and empowerment. The counterculture of the 1960s and early 1970s, particularly in the San Francisco Bay Area, played an unexpected role. Some people in this movement saw computers not as tools of corporate or military power, but as potential instruments of liberation. Stuart Brand, who created the Whole Earth catalog, promoted the idea of personal access to computing tools. Douglas Engelbart, working at Stanford Research Institute, demonstrated in 1968 what became known as the mother of all DMOS, showcasing the mouse, hypertext, video conferencing, and collaborative editing, a vision of interactive personal computing that was decades ahead of its time. But the real breakthrough for personal computing came from an unexpected direction: hobbyists. In the early 1970s, electronic enthusiasts started to realize that integrated circuits were becoming cheap enough that you could build a computer yourself. These weren't practical business machines. They were toys, experiments, learning tools, but they represented something new. Computers built for the love of computing itself, not for any specific practical purpose. The Altair 8800, released in 1975, is often considered the first true personal computer. It was a kit. You assembled it yourself from parts. And when completed, it had 256 bytes of memory, not kilobytes, not megabytes. Bytes, no keyboard, no screen, just switches and lights on the front panel. To program it, you'd flip switches to enter machine code instructions in binary. To see the output, you'd read patterns of blinking lights. By any practical measure, the Altair was nearly useless, but to hobbyists, it was amazing. For less than $400, you could own a computer. You could program it, experiment with it, learn from it. The Altair appeared on the cover of Popular Electronics in January 1975, and orders poured in. The personal computer revolution had begun. Clubs of computer hobbyists sprang up, most famously the Homebrew Computer Club in Silicon Valley. Members shared designs, helped each other debug hardware, and discussed what these machines might eventually become. At one of these meetings, a young man named Steve Wozniak showed off a computer he designed that actually had a keyboard and could display text on a TV screen. His friend Steve Jobs suggested they build them to sell. They called their machine the Apple I. The Apple was still basically a hobbyist machine, but the Apple II, released in 1977, was something different. It was a complete system. Computer, keyboard, power supply, all in one case. It displayed color graphics on a regular television. It had expansion slots so users could add capabilities. It could run software loaded from audio cassettes and later from floppy disks. And crucially, it was sold not as a kit, but as a finished product that regular people could buy and use. The Apple II was successful, but it was a spreadsheet program called VisiCalc that really demonstrated the computer's potential. VisiCalc let users create financial models, spreadsheets with rows and columns of numbers where changing one value would automatically recalculate everything else. For businesses and professionals, this was transformative. Accountants, financial planners, and business managers who'd never imagined they needed a computer suddenly realized these machines could make their work dramatically easier. The Apple II, running VisiCalc, became a business tool. Other companies jumped in. Commodore released the PET in 1977, targeting education and small businesses. Tandy released the TRS-80, sold through Radio Shack stores. These machines were still primitive by modern standards. Tiny amounts of memory, simple graphics, programs stored on cassette tapes. But they were cheap enough and useful enough that ordinary people and small businesses could justify buying them. Then IBM entered the personal computer market in 1981 with the IBM PC. IBM's decision to use an open architecture, publishing technical specifications and allowing other companies to make compatible hardware and software, created an industry standard. While Apple's approach was to control everything about their computers, IBM's approach enabled an ecosystem of compatible machines and software. This openness would eventually make IBM-compatible PCs dominant in business computing, while Apple carved out a niche among creative professionals and enthusiasts who valued the company's integrated design approach. The pace of change was dizzying. Computers that had cost millions of dollars and filled rooms a generation earlier were now being replicated in devices that cost a few $1,000s and fit on desks. Memory was measured in kilobytes instead of bytes. Storage moved from fragile cassette tapes to floppy disks that could hold hundreds of kilobytes. Processors became faster, more capable. Software evolved from simple programs you'd type in yourself, from magazines, to sophisticated applications sold in stores. By the mid-1980s, personal computers were becoming common in offices, schools, and homes. They were still mysterious to many people, still required some technical knowledge to use effectively. But the trajectory was clear. Computers were becoming personal tools, devices that individuals owned and used for their own purposes. The transformation from room-sized machines operated by specialists to personal devices on millions of desks had taken just a couple of decades. The Silicon Revolution had made this possible. The transistor's invention, the development of integrated circuits, and the relentless progress described by Moore's law had driven computers from expensive, fragile, power-hungry machines to affordable, reliable, increasingly powerful devices. The foundation was laid for the next phase, making computers truly easy to use, truly useful for regular people, and eventually truly personal by connecting them together in a global network that would change human civilization. But that's a story for the chapters ahead. Picture a suburban office park in Palo Alto, California, in the early 1970s. Inside a nondescript building, researchers at Xerox PARC, the Palo Alto Research Center, are working on something that will change how humans interact with computers forever. They're not thinking about punch cards or command lines. They're imagining computers as creative tools, as extensions of human thought, as devices that respond to natural gestures and visual thinking. What they created was the Alto, a computer that had something no commercial computer had before, a graphical user interface. Instead of typing cryptic commands, you could use a mouse to point at things on the screen. Instead of lines of text, you had windows that could overlap, icons representing files and programs, menus you could click. The Alto had a high-resolution bitmap display, meaning every pixel could be controlled individually, allowing for graphics, multiple fonts, and visual layouts that resembled actual documents. The Alto was never sold commercially. It was too expensive, too ahead of its time. But Xerox used them internally and shared them with universities. And in December 1979, they made a decision that would change computing history. They invited a delegation from Apple Computer to see what they were working on. Steve Jobs visited PARC and saw the Alto's graphical interface, and something clicked in his mind. He'd been working on personal computers for years, machines that were powerful but still required technical knowledge to use effectively. What he saw at PARC was different. A computer that could be intuitive, that could be understood visually, that regular people could use without training. He left PARC determined to bring this vision to the mass market. The result was the Apple Lisa in 1983, and more importantly, the Macintosh in 1984. The Macintosh was revolutionary not because of its raw power. It had modest specifications by the standards of the time, but because of its interface. You turned it on, and instead of a blinking cursor waiting for commands you'd have to know, you saw a friendly desktop with icons. You used a mouse to point and click. You could see your documents and files represented visually. Windows could be moved and resized. It was, as Apple's advertising proclaimed, the computer for the rest of us. The Macintosh's famous 1984 Super Bowl commercial, directed by Ridley Scott, positioned it as liberation from the conformity of business computing, particularly IBM's dominance. The ad was more about attitude than features, but it captured something real. Personal computers were becoming tools of individual empowerment, not just business equipment. But let's talk about the mouse for a moment, because it represents something important about how we interact with computers. The mouse was invented by Douglas Engelbart in the 1960s as part of his vision for augmenting human intellect. It's such a simple device. It tracks movement and has a button or two, but it creates a direct, intuitive connection between physical motion and digital action. Moving your hand moves a cursor on screen. The connection feels natural, immediate. Xerox PARC refined the mouse and made it central to their interface design. Apple commercialized it, and for decades, the keyboard and mouse became the standard way humans communicated with computers. Think about how strange this is. We were using physical objects from the pre-digital age, keys for typing, a pointing device, to interact with purely digital information. But these physical interfaces made computers accessible in ways that purely abstract command line interfaces never could. The graphical user interface democratized computing. You didn't need to memorize commands or understand file systems. You could learn by exploring, by clicking on things to see what they did. Children could use computers. Artists could use computers. Writers could use computers. The machine adapted to human ways of thinking rather than humans having to adapt to the machine's logic. Microsoft, watching Apple's success with graphical interfaces, began developing Windows, a graphical environment that would run on IBM-compatible PCs. The first versions were crude, but Windows gradually improved, and by Windows 3 in 1990, and especially Windows 95, Microsoft had created a graphical interface that brought millions more users into computing. The combination of relatively inexpensive IBM-compatible hardware and Windows software made graphical personal computing accessible to businesses and homes worldwide. The 1980s and early 1990s saw personal computers becoming genuinely useful tools for regular people. Word processors like WordPerfect and later Microsoft Word made writing and editing documents easier than typewriters ever were. Spreadsheet programs like Excel made financial analysis accessible. Desktop publishing software like PageMaker meant you could design professional-looking documents on a computer that sat on your desk. Games became more sophisticated, providing entertainment alongside productivity. Computing was also becoming more personal in a literal sense. In the 1980s, computers were still primarily shared. One computer per household, used by different family members at different times. But as prices continued to fall and capabilities increased, many families began having multiple computers. Teenagers had computers in their bedrooms. Adults had computers at work and at home. The computer was shifting from a shared appliance to a personal device. But even as computers became more capable and easier to use, they were still isolated islands. If you wanted to share a file with someone, you'd copy it onto a floppy disk and physically hand them the disk. If you wanted to communicate, you'd write a letter or make a phone call. The idea that computers might be connected together, forming networks that could share information and enable communication, was being explored by researchers and enthusiasts, but it hadn't yet reached most computer users. The stage was set for the next transformation, one that would be even more profound than the personal computer revolution itself. Computers were about to stop being isolated calculating machines and become windows into a connected digital world. But before we get there, we need to understand how that network came to exist, how a military research project would evolve into the most significant communication system humans had ever created. That's where our journey takes us next. Before we talk about networks and the internet, let's take a moment to appreciate something we often overlook: how profoundly the way we interact with computers has evolved. This might seem like a side story, but it's actually central to understanding how computers went from specialist tools to everyday objects that billions of people carry in their pockets. In the beginning, there was the command line. You'd sit at a computer terminal, in the early days, literally a teletype machine connected to a mainframe, and type commands. If you wanted to see a list of files, you'd type something like dir or ls, depending on your operating system. If you wanted to run a program, you'd type its name. If you wanted to do anything, you had to know the exact command with the correct syntax, spelled correctly. The command line was powerful. Experienced users could chain commands together, creating complex operations with a few keystrokes. Programmers and system administrators loved it because it gave them precise control and could be scripted for automation. But it was also unforgiving. Make a typo, forget a required parameter, or use incorrect syntax, and you'd get an error message that might or might not help you understand what went wrong. For people who spent hours every day working with computers, learning these commands was worthwhile. They'd internalize the syntax, develop muscle memory for common operations, and become fluent in this textual language. But for casual users or for tasks that didn't require such precision, the command line was a barrier. You couldn't explore, you couldn't experiment, you had to know what to do before you did it. The graphical user interface changed this fundamentally. With a GUI, you could see your options. Menus showed available commands. Icons represented programs and files visually. Dialog boxes guided you through complex operations, showing options and explaining choices. You could undo mistakes. You could preview changes before committing to them. The computer became explorable, forgiving, visual. But creating good graphical interfaces is harder than it looks. Early GUIs were often clunky, with confusing icons, poorly organized menus, and interactions that didn't match users' mental models. Designers had to figure out visual metaphors that made sense. The desktop metaphor with files in folders, the trash can for deletion, windows that could be moved and resized like papers on a physical desk. Human-computer interaction became a field of study. Researchers investigated how people thought about tasks, what visual elements they found intuitive, how to minimize cognitive load and reduce errors. They studied eye movements, measured task completion times, conducted usability tests. Good interface design combined psychology, graphic design, and technical implementation. Consider something as simple as the save icon, traditionally a floppy disk. For users who grew up with floppy disks, this makes intuitive sense. But for people who have never seen a physical floppy disk, it's an arbitrary symbol that has to be learned. Interface design is full of these decisions, conventions that develop and persist even after their original metaphors become obsolete. The mouse wasn't the only input innovation. Graphics tablets allowed artists to draw directly on computers, translating stylus pressure and angle into digital marks. Touchpads on laptops provided pointing without requiring a separate mouse. Trackballs, which were essentially upside-down mice, offered precise control in limited space. Each input method had advantages for different tasks and users. Gaming drove some interface innovations. Joysticks, game controllers, steering wheels, light guns, devices designed to make playing games feel natural and responsive. The Nintendo Entertainment System's controller, with its directional pad and buttons, established a layout that influenced game controllers for decades. Later, motion-sensing controllers like the Nintendo Wii Remote and camera-based systems like the Xbox Kinect explored whole-body interfaces, where your physical movements directly controlled on-screen action. Accessibility was another driver of interface evolution. Not everyone can use a mouse. Not everyone can see a screen. Not everyone can hear audio cues. Developers created alternative input methods. Keyboard navigation for mouse alternatives, screen readers that convert text to speech, voice control systems, eye-tracking technology that lets people control computers by looking at different areas of the screen. These accessibility technologies often benefited everyone. Voice control, initially designed for people who couldn't use keyboards, became convenient for hands-free operation while driving or cooking. Voice interfaces represent a particularly interesting evolution. Early speech recognition systems were limited and frustrating, requiring careful enunciation and often misunderstanding commands. But as machine learning improved, voice recognition became more accurate and natural. Digital assistants like Apple's Siri, Amazon's Alexa, and Google Assistant made voice interaction practical for everyday tasks. You could ask questions, set reminders, control smart home devices, all through natural language. This shift to voice represents something profound. For decades, we adapted to computers, learning their languages and conventions. Voice interfaces make computers adapt to us, understanding human language with all its ambiguity and variation. It's not perfect. Voice assistants still misunderstand, still struggle with accents and context. But it's moving toward the science fiction ideal of computers that understand natural human communication. Touchscreens created another revolution in interface design. The concept wasn't new. Touch-sensitive displays existed for decades in specialized applications. But they were expensive, imprecise, and fragile. The breakthrough came with capacitive touchscreens that could detect multiple simultaneous touches and respond to gestures. Pinching to zoom, swiping to scroll, tapping to select. When the iPhone launched in 2007 with its multi-touch interface, it demonstrated how powerful direct manipulation could be. Instead of using a mouse or stylus to point at virtual buttons, you touched the buttons themselves. Instead of clicking and dragging to scroll, you pushed the content directly with your finger. and it moved, even continuing to scroll with momentum after you lifted your finger, mimicking the physics of pushing a physical object. Touch interfaces required rethinking design. Buttons needed to be larger to accommodate imprecise finger taps. Menus had to be reorganized. New gestures had to be discoverable. How do users learn that pinching zooms or that swiping from the edge reveals hidden menus? Apple and Google developed design guidelines, and conventions gradually emerged that most touchscreen apps followed. The iPad, launched in 2010, further demonstrated touch interfaces' potential. On a larger screen, multi-touch enabled creative applications. Drawing apps where you could use multiple fingers simultaneously, music apps that turned the screen into instruments, productivity apps that used gestures to navigate and edit documents. The directness of touch, where your finger was literally touching the thing you wanted to manipulate, made certain tasks more intuitive than they'd ever been with mice and keyboards. But interestingly, touch didn't completely replace traditional interfaces. For tasks requiring precision, detailed photo editing, programming, complex data entry, keyboards and mice remained superior. Graphic designers still used tablets with pressure-sensitive styluses. Writers preferred physical keyboards for extended typing. The best interface depends on the task, and rather than one interface replacing another, we ended up with diverse input methods suited to different purposes. Augmented and virtual reality represent the latest frontier in interface evolution. VR headsets create immersive 3D environments where you can look around naturally and interact with virtual objects using hand controllers or tracked gloves. AR systems overlay digital information on the physical world, potentially letting you interact with virtual controls as if they existed in physical space. These technologies are still developing. Current VR headsets are bulky, can cause motion sickness, and isolate users from their physical surroundings. AR systems struggle with tracking and registration, aligning virtual objects precisely with real-world references. But the potential is clear. Interfaces that engage our spatial reasoning and physical intuitions, making digital interactions feel as natural as manipulating physical objects. The evolution of computer interfaces reveals a constant tension between power and accessibility, between giving experts sophisticated control and making systems usable for everyone. Command lines still exist because they're powerful and efficient for certain tasks. Graphical interfaces dominate because they're explorable and forgiving. Voice and touch interfaces are growing because they're natural and immediate. The future likely involves all these interfaces coexisting, with people choosing the input method that works best for their current task and personal preferences. What's remarkable is how quickly these changes have occurred and how readily people adapt. Someone who learned computing on command line systems in the 1980s might have been skeptical about graphical interfaces, yet most eventually adapted. People who grew up with mice and keyboards learned touch interfaces within minutes of picking up a smartphone. Humans are remarkably flexible in how we interact with tools, as long as those tools respect our capabilities and limitations. Imagine it's 1995 and you're sitting at your computer, listening to the distinctive screech and warble of a dial-up modem connecting to the internet. It takes 30 seconds, sometimes a minute. You can't use the phone while you're online. The connection is slow. Loading a single image might take 30 seconds. But despite these limitations, you're experiencing something magical. Your computer is no longer an isolated machine. It's a window into a connected world. But the story of how we got to this point begins much earlier, in the late 1960s, with a military research project that was trying to solve a problem about communication in a world where nuclear war seemed like a real possibility. The U.S. Department of Defense wanted a communication network that could survive partial destruction. Traditional telephone networks were vulnerable. Cut a key connection, and you could isolate entire regions. What they needed was a distributed network where information could find alternate routes if some connections were destroyed. Researchers at ARPA, the Advanced Research Projects Agency, began working on this problem. The solution they developed was packet switching. Instead of establishing a dedicated circuit between 2 points for the duration of a communication, as phone systems did, packet switching breaks information into small packets that each find their own way through the network. If one route is blocked, packets take a different path. When they all arrive at the destination, they're reassembled into the original message. In 1969, ARPANET went live with 4 connected computers at different universities. The first message sent was supposed to be login, but the system crashed after transmitting just low. It's a fitting beginning. Computers failing, but the idea working. ARPANET grew, connecting more universities and research institutions. Researchers used it to share files, send messages, and access remote computers. Email emerged as one of ARPANET's most popular applications. Ray Tomlinson implemented the first email system in 1971, choosing the @ symbol to separate usernames from host names, a convention we still use today. Email wasn't considered particularly important by ARPANET's designers, but users immediately grasped its value. Being able to send messages that would wait for the recipient rather than requiring both people to be present simultaneously was transformative. Through the 1970s and 1980s, various networks developed. ARPANET for research, BitNet connecting universities, Usenet for discussion groups, commercial networks like CompuServe and America Online. These networks initially couldn't communicate with each other. They were like islands, internally connected but isolated from other islands. The solution was a set of protocols, standardized rules for how computers communicate, that would let different networks interconnect. The key protocols, TCP/IP, Transmission Control Protocol/Internet Protocol, were developed by Vint Cerf and Bob Kahn in the 1970s. TCP/IP provided a common language that any network could use to exchange information with any other network. When ARPANET officially switched to TCP/IP on January 1, 1983, this date is often considered the birth of the Internet. A network of networks, all able to communicate using shared protocols. But the Internet remained primarily a tool for academics, researchers, and technically sophisticated enthusiasts through the 1980s. It was still text-based, still required technical knowledge to use, still arcane and intimidating to regular people. What transformed the Internet from a specialist tool into a mass medium was the World Wide Web. In 1989, Tim Berners-Lee, a British scientist working at CERN, the European Physics Laboratory, proposed a system for sharing information between researchers. His idea was elegant. Documents could contain hyperlinks to other documents. You'd click on a link, and you'd be taken to the linked document, which might be on a different computer anywhere in the world. The location would be specified by a URL, Uniform Resource Locator, a standard way of addressing resources on the Internet. Berners-Lee created the first web browser and web server in 1990. He wrote the hypertext markup language, HTML, that defined how web pages were structured. He specified the Hypertext Transfer Protocol, HTTP, that governed how web browsers and servers communicated. And crucially, he convinced CERN to place these technologies in the public domain, free for anyone to use and build upon. The web grew slowly at first. In 1993, there were only about 130 websites. But that year saw the release of Mosaic, the first web browser that was both powerful and easy to use. Mosaic displayed images inline with text, making web pages visually rich. It ran on various computer platforms. It was free. Mark Andreessen and Eric Bina, students at the University of Illinois, created Mosaic, and it showed people what the web could be. Andreessen would go on to found Netscape, whose Navigator browser would dominate the mid-1990s. The browser wars between Netscape and Microsoft's Internet Explorer drove rapid development of web technologies. Each browser added features, competed for users, and pushed the capabilities of what web pages could do. This competition had downsides. Browsers became incompatible. Websites would work differently or not at all depending on which browser you used. But it also drove innovation. By the mid-1990s, going online was becoming accessible to regular people. Internet service providers offered dial-up connections for monthly fees. AOL mailed millions of CD-ROMs to homes, offering easy sign-up for their service. CompuServe, Prodigy, and other services competed for users. The distinctive sound of a modem connecting became familiar in millions of homes. What did people do online? They browsed websites, marveling at the ability to access information from around the world. They sent email to friends and family, often people they'd lost touch with but could now reconnect with regardless of distance. They joined discussion forums and chat rooms, finding communities of people who shared their interests. They played early online games. They shopped, tentatively at first, wondering if it was safe to enter credit card information on websites. The early web was text-heavy and slow, but it was also exciting and democratic. Anyone could create a website. GeoCities, launched in 1994, offered free web hosting and simple tools for creating personal pages. Millions of people created websites about their hobbies, their pets, their lives. These sites often looked amateurish by modern standards. Clashing colors, animated GIFs, auto-playing MIDI music. But they represented something important. Regular people could publish to the world. Search engines emerged as essential tools for navigating the growing web. Early directories like Yahoo had humans categorizing websites, but as the web grew exponentially, human curation couldn't keep up. Automated search engines like AltaVista, Lycos, and Excite indexed web pages and ranked results by various algorithms. In 1998, Google launched with a new approach, ranking pages by how many other pages linked to them, treating links as votes of confidence. Google's simple interface and relevant results quickly made it dominant. E-commerce transformed from experiment to industry. Amazon, founded in 1995 as an online bookstore, demonstrated that people would buy products over the internet if the experience was convenient and trustworthy. eBay, launched the same year, created a marketplace where individuals could buy and sell items through online auctions. These companies and others figured out logistics, payment processing, and trust mechanisms that made online commerce practical. The dot-com boom of the late 1990s saw enormous investment in internet companies, often based on optimistic assumptions about how quickly online business models would become profitable. The bust in 2000 to 2001 deflated many of these assumptions, leading to the collapse of numerous internet companies and the loss of billions in investment. But the underlying infrastructure survived, and the lessons learned informed the next generation of internet businesses. Social networking emerged as a powerful use of the connected web. Early services like Friendster and MySpace let people create profiles, connect with friends, and share updates about their lives. Facebook, launched in 2004 and initially limited to college students, would eventually become the dominant social network with billions of users worldwide. These platforms transformed the internet from a place you went to find information or buy things into a space where you maintained relationships and shared your life. The internet changed computers from calculating and productivity tools into communication and connection devices. The most valuable applications weren't spreadsheets or word processors anymore. They were email, web browsers, social networks, messaging apps. Computers were becoming less about manipulating information and more about connecting with other people and accessing shared knowledge. Broadband connections, replacing slow dial-up modems in the 2000s, made the online experience dramatically better. Always-on connections meant you didn't have to wait for modems to connect. Higher speeds made multimedia content practical, streaming music, watching videos, video calls. The internet was evolving from a text-based medium into a rich multimedia environment. YouTube, launched in 2005, demonstrated the internet's potential for video sharing. Wikipedia, starting in 2001, showed how collaborative knowledge creation could produce a comprehensive encyclopedia available to everyone for free. iTunes and later Spotify changed how people accessed music. Netflix evolved from DVD rentals to streaming, transforming how people watched television and movies. The internet had become infrastructure, as fundamental to modern life as electricity or running water. Businesses depended on it, education incorporated it, government services moved online, social movements organized through it. Dating, shopping, learning, entertainment, communication all had online components or were fully digital. But this transformation brought challenges too. Privacy concerns grew as companies collected data about users' activities. Security became crucial as financial transactions and personal information moved online. The digital divide meant that people without internet access were increasingly disadvantaged. Misinformation and manipulation became easier as content could spread globally in seconds. The same technologies that enabled connection also enabled surveillance and control. The internet was originally designed as an open, distributed system without central control. This openness enabled innovation and free expression, but it also created problems: spam, hacking, copyright infringement, illegal content. Governments struggled with how to regulate online activities without stifling innovation or violating free speech principles. Questions about censorship, liability, and jurisdiction remain contentious. What's remarkable is how quickly the internet went from a specialized research network to essential global infrastructure. In just 3 decades, it became indispensable for billions of people, and this transformation set the stage for the next revolution. Making internet access mobile, putting connected computers into devices people carried everywhere, creating a world where being online wasn't something you did at a desk. It was simply the default state of existence. Let's go back to the early 1980s for a moment. If you wanted to compute while traveling, your options were limited. You could bring a portable computer. The Osborne 1, released in 1981, was technically portable in that it had a handle, but it weighed 24 pounds and was the size of a small suitcase. The screen was tiny, the keyboard cramped. You'd need to plug it in because the battery life was measured in minutes. This was portable only in the most generous sense of the word. The desire for truly mobile computing was obvious. Business travelers wanted to work on planes or in hotels. Students wanted to take notes on computers in class. People wanted to compute anywhere, not just at desks. But the technology wasn't ready. Batteries were heavy and inefficient. Displays consumed too much power. Storage required bulky hard drives. The components that made desktop computers practical were too large, power-hungry, or fragile for truly portable devices. Throughout the 1980s, manufacturers tried various approaches. Luggable computers were lighter than the Osborne, but still not practical for regular transport. Handheld devices existed, but they were specialized. Calculators, electronic organizers, portable games. Laptops improved gradually, becoming lighter and more capable, but they remained expensive and limited. The Apple PowerBook, released in 1991, established the modern laptop form factor. Screen in the lid, keyboard toward the back of the base, trackball, later trackpad, in front of the keyboard for palm rest positioning. This design made sense ergonomically and became the standard that most laptops still follow. But PowerBooks were expensive, and battery life was still measured in hours at best, often less with active use. PDAs, personal digital assistants, represented another approach to mobile computing. Devices like the Apple Newton and Palm Pilot were pocket-sized, meant for managing contacts, calendars, and notes. The Newton, released in 1993, had handwriting recognition that was supposed to let you write with a stylus directly on the screen. The technology wasn't quite ready, and the Newton became infamous for misreading handwriting, even becoming the subject of jokes on The Simpsons. The Palm Pilot, released in 1996, was more successful. It had a simpler interface, better handwriting recognition, using a special streamlined alphabet called graffiti, and synchronized with desktop computers to share data. Millions of people carried Palm Pilots, using them to manage schedules and contacts. But they were still separate devices, additions to your toolkit rather than replacements for anything. Mobile phones were evolving on a parallel track. The first generation of cell phones in the 1980s were bulky, expensive devices with terrible battery life. The famous Motorola Dynatac 8000X, released in 1984, was nicknamed the Brick for obvious reasons. It weighed 2 pounds and cost nearly $4,000. You could talk for about 30 minutes before the battery died, and charging took 10 hours. But cellular technology improved. Phones became smaller, lighter, cheaper. By the late 1990s, millions of people carried mobile phones. They were still primarily voice devices. You could call people and, increasingly, send short text messages using SMS. Some phones had simple games or basic organizer features, but they weren't computers in any meaningful sense. The idea of combining a mobile phone with a PDA seemed obvious. Several companies tried, creating devices that could make calls and manage data. The BlackBerry, introduced in 1999, found success with business users by offering push email. Messages arrived automatically rather than requiring manual checking, and a physical keyboard that made typing relatively easy. BlackBerry devices became ubiquitous among business professionals, who nicknamed them crackberries because of how addictive constant email access became. But these devices were still fundamentally limited. Their screens were small, their processing power was minimal, their software was basic, they were useful for specific tasks, email, calendars, messaging, but they weren't general-purpose computers. You couldn't really browse the web well, couldn't watch videos, couldn't run sophisticated applications. On January 9, 2007, Steve Jobs walked onto a stage in San Francisco and announced that Apple was releasing 3 revolutionary products: a widescreen iPod with touch controls, a revolutionary mobile phone, and a breakthrough internet communications device. Then he revealed these weren't 3 separate devices. They were one device called iPhone. The original iPhone seems modest by modern standards. It had a 3.5-inch screen, 4 GB or 8 GB of storage, a 2-megapixel camera, and couldn't run third-party applications at launch. It lacked features that other phones had. No video recording, no copy and paste, no flash support for websites. It was expensive, at $499 with contract for the cheapest model. But several things made it revolutionary. The multi-touch interface made interactions intuitive and direct. The screen dominated the front of the device, with minimal physical buttons. The full web browser made internet access practical rather than frustrating. The design was elegant. The integration between hardware and software created an experience that felt cohesive and polished. More importantly, Apple was positioning the iPhone not as a phone with computer features, but as a computer that happened to include phone functionality. This conceptual shift mattered. Previous smartphones were phones with add-on capabilities. The iPhone was a pocket computer with wireless connectivity, and making phone calls was just one of its applications. In 2008, Apple released the App Store, allowing third-party developers to create applications for iPhone. This transformed the device. Suddenly, anyone could program for iPhone and distribute their apps globally. Within months, thousands of apps were available. Within years, hundreds of thousands. The iPhone became a platform, and the creativity of developers worldwide defined what it could do. Google, seeing the threat Apple's iPhone posed, accelerated development of Android, a mobile operating system they'd acquired and been working on. The first Android phone launched in 2008. Unlike Apple's closed approach, Android was open source and available to any manufacturer who wanted to use it. This openness led to Android becoming dominant by market share, running on phones from Samsung, LG, Motorola, and dozens of other manufacturers. The smartphone revolution happened remarkably quickly. In 2007, smartphones were niche devices for business users and early adopters. By 2010, they were mainstream. By 2015, they were ubiquitous in developed countries and spreading rapidly in developing nations. The transition from "some people have smartphones" to "everyone has a smartphone" took less than a decade. What made smartphones so successful? They consolidated multiple devices: phone, camera, music player, GPS, web browser, email device, game console, into one pocket-sizable item. They were always with you, always connected. They could be customized with apps for any purpose you could imagine. They had excellent design and user experience. And they became central to social connection through social media, messaging, and communication apps. Smartphones changed behavior in ways that seem obvious now, but were surprising at the time. People stopped carrying cameras because phone cameras became good enough. MP3 players disappeared as phones absorbed music playback. Dedicated GPS devices became obsolete. E-readers struggled as phones and tablets offered reading alongside everything else. Even watches were affected as people pulled out phones to check the time. The social changes were profound. People were now always reachable, always online. Social media became constant rather than something you checked when sitting at a computer. Photos became ephemeral and abundant rather than precious and rare. Navigation became trivial with turn-by-turn directions in your pocket. Information access became immediate. Whenever you had a question, you could look it up instantly. Tablets represented a middle ground between smartphones and laptops. The iPad, launched in 2010, created the modern tablet category. Larger screens than phones but more portable than laptops, tablets were excellent for consuming content. Reading, watching videos, browsing, while being acceptable for lighter creation tasks. They found niches in education, healthcare, retail, and as home devices for casual computing. Mobile computing enabled entirely new categories of applications. Ride-sharing like Uber and Lyft relied on smartphones for requesting rides, showing driver locations, and handling payments. Food delivery services used phones to let customers order and track deliveries. Mobile banking apps made finance more accessible. Health and fitness apps leveraged phone sensors to track activity and wellness. Dating apps put potential partners in your pocket. Games used touchscreens, accelerometers, and GPS to create experiences impossible on traditional platforms. The always-on, always-connected nature of smartphones also created problems. Distracted driving became a major safety issue. Attention fragmentation, constantly checking phones, unable to focus deeply on single tasks, affected productivity and well-being. Social media on phones facilitated cyberbullying and social comparison that impacted mental health, particularly among young people. Privacy concerns intensified as phones tracked location, logged activities, and collected personal data. Smartphone addiction became recognized as a genuine issue. The devices were designed to be engaging, using psychological principles like variable reward schedules to keep users checking for updates, messages, and notifications. Companies competed for user attention, optimizing apps to maximize engagement time. Many people found themselves compulsively checking phones hundreds of times per day, feeling anxious when separated from their devices. The digital divide took on new dimensions. While smartphones made computing accessible in ways that expensive desktop computers never could, helping bring internet access to developing countries, they also created new inequalities. People who could only access the internet through phones with small screens and limited data plans had different online experiences than those with unlimited broadband and large devices. Access to information and services became stratified by device quality and connectivity. Mobile computing also changed what we expect from computers. We expect them to be immediately responsive with no boot-up time. We expect them to work everywhere with constant connectivity. We expect them to know our location and provide context-aware services. We expect intuitive touch interfaces rather than mice and keyboards. The smartphone experience has influenced how we think about all computing. Looking at the evolution from room-sized mainframes to pocket supercomputers in just a few decades is dizzying. The smartphone in your hand has more computing power than the systems that guided Apollo missions to the moon. It has instant access to more information than the largest library held a generation ago. It can photograph, record video, navigate, communicate, entertain, educate, and perform thousands of specialized functions through apps. It's a product of decades of miniaturization, improved batteries, better displays, faster processors, and countless engineering innovations. And we're still in the early stages of mobile computing. Wearable devices like smartwatches extend smartphone functionality to even more convenient form factors. Wireless earbuds with processing power and sensors are becoming smarter. Augmented reality glasses promise to overlay digital information on the physical world. The trajectory toward more intimate, more ambient computing continues. The smartphone era showed us that computers don't have to look like computers. They can be any form factor with any interface designed for any purpose. The general-purpose computer that can be programmed to do anything has been packaged into forms we carry, wear, speak to, and increasingly barely notice. Computing has become invisible, embedded so thoroughly in our tools and environment that we don't think of using computers. We just interact with the world, and the computation happens seamlessly in the background. Picture an arcade in 1972. Among the pinball machines and jukebox, there's something new. A black cabinet with a screen showing two white rectangles that can move up and down, and a square dot bouncing between them. The game is called Pong, and it's mesmerizing in its simplicity. Two players turn knobs to control the paddles, trying to bounce the ball past their opponent. That's it. That's the entire game, and people are lining up to play it. Pong wasn't actually the first video game. That honor probably belongs to Space War, created by MIT students in 1962, or Tennis for Two, a physics demonstration from 1958. But Pong was the first video game to become a commercial success, the first to show that people would pay money to play interactive games on screens. It was created by Nolan Bushnell's company Atari, and it launched an industry. The early arcade games were simple by necessity. The technology was limited, so games had to be built around basic concepts that were immediately understandable and addictively playable. Space Invaders, released in 1978, had players shooting at rows of descending aliens. Pac-Man, in 1980, was about navigating a maze while eating dots and avoiding ghosts. Donkey Kong, in 1981, introduced a character named Jumpman, later renamed Mario, who had to rescue a damsel from a giant ape by climbing girders and avoiding obstacles. These games were cultural phenomena. Space Invaders supposedly caused a temporary shortage of 100 yen coins in Japan. Pac-Man became a global icon with merchandise, a cartoon series, and even a hit song. Arcades became social spaces where teenagers gathered, competed for high scores, and mastered games through repeated play. The best players achieved local celebrity status. But gaming also drove technical innovation in ways that influenced all computing. Games demanded faster processors, better graphics, more memory, and responsive input. Game developers pushed hardware to its limits, finding clever tricks to make machines do things they weren't designed for. This pressure to improve performance for gaming benefited all computer applications. Home gaming consoles brought interactive entertainment into living rooms. The Atari 2600, released in 1977, let families play games like Space Invaders and Pac-Man at home. The Nintendo Entertainment System, launched in North America in 1985 after the video game crash of 1983, revitalized home gaming with titles like Super Mario Bros., The Legend of Zelda, and Metroid. Sega's Genesis and later Sony's PlayStation competed, driving innovation through competition. But let's talk about graphics specifically, because the evolution of computer graphics is one of the most visible transformations in computing history. Early computers had no graphics at all, just text on screens or printouts. When graphics appeared, they were simple, monochrome displays showing blocky characters and basic shapes. Color was expensive and limited to a small palette. The Apple II, released in 1977, was one of the first affordable computers with color graphics capabilities. It could display high-res graphics with 6 colors and low-res graphics with 16 colors. This seems primitive now, but at the time, seeing colorful images on a personal computer screen was remarkable. Game developers and hobbyists explored what could be done with these limited capabilities, creating games, educational programs, and artistic works. The Commodore Amiga, released in 1985, represented a significant leap in graphics capabilities for home computers. It could display thousands of colors simultaneously, had hardware support for sprites and scrolling, and included dedicated graphics coprocessors. The Amiga became beloved by game developers and digital artists, who appreciated its advanced graphics capabilities at a relatively affordable price. But the real transformation in computer graphics came with 3D rendering. Displaying three-dimensional objects on two-dimensional screens requires complex mathematical calculations. Projecting 3D coordinates onto a 2D plane, determining which surfaces are visible, calculating lighting and shading, rendering textures. Early 3D games used simple wireframe graphics or flat-shaded polygons because computers weren't powerful enough for more sophisticated rendering. The development of dedicated graphics cards changed this. Instead of the main processor handling graphics calculations, specialized hardware designed specifically for rendering could perform these operations much faster. 3DFX's Voodoo cards in the mid-1990s brought hardware-accelerated 3D graphics to consumer PCs, enabling games with textured polygons, perspective-correct rendering, and smooth animation. NVIDIA and ATI, later acquired by AMD, became the dominant graphics card manufacturers, competing to produce faster, more capable cards with each generation. Modern graphics cards contain thousands of processing cores optimized for the parallel calculations required for rendering. They're essentially specialized computers dedicated entirely to creating images. The evolution of 3D graphics in games is stunning to observe. Compare an early 3D game like Doom 1993, which used clever tricks to simulate 3D environments while actually rendering 2D sprites, to a modern game with photorealistic lighting, detailed textures, realistic physics, and environments containing millions of polygons. The progression happened over just 3 decades. Game developers pushed graphics technology forward by demanding ever more realistic rendering. They wanted dynamic lighting where shadows moved naturally as light sources changed. They wanted realistic water with reflections and refraction. They wanted characters with detailed faces showing subtle expressions. They wanted vast open worlds players could explore seamlessly. Each of these goals required innovations in graphics hardware and software. Ray tracing represents the current frontier in real-time graphics. Instead of using approximations and tricks to simulate how light behaves, ray tracing actually calculates light paths, bouncing rays through a scene to determine what each pixel should show. This produces incredibly realistic lighting, reflections, and shadows, but it's extremely computationally expensive. Modern graphics cards are finally powerful enough to perform ray tracing in real time for games, bringing movie-quality rendering to interactive experiences. Gaming also drove improvements in other hardware components. Sound cards evolved to provide 3D positional audio, helping players locate enemies by sound. Controllers became more sophisticated, adding analog sticks for precise control, force feedback to provide tactile sensations, and motion sensing for physical interaction. Storage requirements grew from games that fit on floppy disks to modern titles requiring over 100 gigabytes of space. The social aspects of gaming evolved too. Early games were solitary experiences or local multiplayer where people shared a screen. Network gaming, starting with LAN parties where people brought computers to the same location to connect them, expanded to online gaming where players worldwide competed or cooperated in real time. MMORPGs, massively multiplayer online role-playing games, like World of Warcraft, created persistent virtual worlds where millions of players interacted. Esports transformed gaming from casual hobby to spectator sport and professional career. Competitive gaming tournaments filled arenas with thousands of spectators and millions watching online streams. Top players earned significant incomes from prize money, sponsorships, and streaming. Games like League of Legends, Dota 2, and Fortnite became cultural phenomena with player bases in the tens of millions. Streaming platforms like Twitch made watching others play games a major form of entertainment. Millions of people regularly watch streamers play games, providing commentary, interacting with chat, and building communities. Some streamers became celebrities with millions of followers. The line between playing games and watching games blurred. Mobile gaming brought interactive entertainment to billions of people who never owned consoles or gaming. Simple games like Angry Birds and Candy Crush reached massive audiences by being free or cheap, immediately accessible, and designed for short play sessions. More sophisticated mobile games like Pokémon Go used GPS and cameras to blend gaming with the physical world. Virtual reality gaming represents an ongoing frontier. VR headsets create immersive 3D environments where you look around naturally and interact with virtual objects. The sense of presence, feeling like you're actually inside the game world, can be powerful. But VR gaming faces challenges. Headsets are expensive, can cause motion sickness, require significant space, and isolate players from their physical surroundings. The technology continues improving, but widespread adoption remains elusive. What's remarkable about gaming's influence on computing is how it made powerful hardware accessible to consumers. Professional graphics workstations for 3D modeling and rendering cost tens of thousands of dollars. But a gaming PC with comparable graphics capabilities cost a fraction of that, subsidized by the enormous gaming market. Gamers willing to pay for better experiences drove production volumes that made powerful hardware affordable. Gaming also changed how we think about computers. They're not just productivity tools or communication devices. They're entertainment systems, creative platforms, social spaces. The interactivity that computing enables, responding to user input in real time, creating experiences rather than just presenting information, is most obvious in games. And gaming pushed the boundaries of what computers could do creatively. Game designers combined storytelling, visual art, music, interaction design, and programming to create experiences that are distinctly of the digital medium. Games can't exist in other forms. They're native to computing in ways that word processors, replicating typewriters, or email replicating letters are not. The innovations driven by gaming, faster processors, better graphics, improved audio, more responsive input, network multiplayer, virtual reality, benefit all computing. When you watch a high-resolution video, use a graphics-intensive application, or experience smooth animations in an interface, you're benefiting from technology developed or refined for gaming. The pursuit of interactive entertainment has been one of computing's most powerful drivers of innovation. Let's travel back to 1950 to a paper published by Alan Turing titled Computing Machinery and Intelligence. Turing, the same mathematician who helped break German codes during World War II and who laid theoretical foundations for computing, posed a question: can machines think? Rather than getting bogged down in philosophical debates about what thinking means, Turing proposed a practical test. Imagine a person having text conversations with two entities, another human and a machine. If the person can't reliably determine which is which based on the conversations, then the machine has demonstrated intelligence in a meaningful sense. This became known as the Turing test, and it set a goalpost for artificial intelligence that still influences the field today. The term artificial intelligence was coined in 1956 at a conference at Dartmouth College, where researchers gathered to explore whether machines could be made to simulate every aspect of learning and intelligence. There was tremendous optimism. Some researchers predicted that within a generation, machines would be as intelligent as humans. They were wrong about the timeline. AI turned out to be much harder than expected, but they were right about the direction. Early AI research focused on problems that seemed to require intelligence. Playing chess, proving mathematical theorems, understanding natural language, recognizing patterns. The approaches varied, but many relied on symbolic reasoning, representing knowledge as symbols and manipulating those symbols according to logical rules. Chess became an important testing ground for AI. Chess seemed like it required deep thinking, strategic planning, and creativity. In 1956, researchers predicted that within 10 years, a computer would be the world chess champion. It actually took 40 years. In 1997, IBM's Deep Blue defeated world champion Garry Kasparov in a 6-game match. Deep Blue didn't think about chess the way humans do. It used brute force search, evaluating millions of positions per second. But it was effective, and it demonstrated that computers could exceed human performance in domains previously considered quintessentially intellectual. Expert systems represented another early AI approach. These were programs that captured the knowledge of human experts in specific domains: medical diagnosis, geological exploration, computer configuration, and used logical reasoning to solve problems. MYCIN, developed in the 1970s, could diagnose blood infections and recommend antibiotics, sometimes performing as well as human experts. These systems showed practical value but were brittle. They only worked in narrow domains and couldn't learn or adapt. The early decades of AI research saw cycles of excitement and disappointment. Breakthroughs would lead to inflated expectations. Then, when systems failed to generalize or encountered unexpected difficulties, funding would dry up and interest would wane. These periods became known as AI winters, times when the field fell out of favor and progress slowed. The challenge was that many tasks humans find easy, recognizing faces, understanding speech, grasping context, moving through complex environments, turned out to be incredibly difficult for computers. Meanwhile, tasks humans find difficult, complex calculations, perfect memory recall, playing chess, were relatively straightforward for computers. This paradox revealed that human intelligence operates differently than early AI researchers had assumed. The breakthrough that would eventually transform AI was an old idea finally getting powerful enough to work: neural networks. Inspired loosely by how biological neurons in brains connect and activate, artificial neural networks consist of layers of simple processing units that pass signals to each other with varying strengths. When you show a neural network examples, images labeled cat or not cat, for instance, and adjust the connection strengths based on whether the network's output is correct, the network gradually learns to recognize patterns. Neural networks were proposed as early as the 1940s, but training them was computationally expensive, and they didn't work particularly well with the limited computing power and small datasets available. Through the 1980s and 1990s, neural networks remained a niche approach, interesting but not demonstrably better than other techniques for most problems. The transformation came around 2010 when several factors converged. Much more powerful computers, especially graphics cards that could perform the parallel calculations neural networks required. Much larger datasets, enabled by the internet and digital photography, and refined training techniques, particularly for deep neural networks with many layers. Deep learning, as this approach became known, suddenly started achieving remarkable results. In 2012, a deep learning system won an image recognition competition by a huge margin, correctly identifying objects in photographs with unprecedented accuracy. Speech recognition, which had been improving gradually for decades, suddenly made a leap forward, becoming accurate enough for practical use. Machine translation between languages, long a frustrating problem, improved dramatically. What made deep learning different was that these systems learned patterns directly from data, rather than requiring humans to explicitly program rules. You didn't have to tell the system what features defined a cat. The network figured it out through training on thousands of cat photos. This made deep learning applicable to messy, complex problems where explicitly stating rules was impractical. The applications proliferated rapidly. Image recognition enabled computers to identify objects, faces, scenes, and activities in photos and videos with human-level or better accuracy. Speech recognition became accurate enough that voice assistants like Siri, Alexa, and Google Assistant became practical. Language translation improved to where it could capture meaning and context, not just word-by-word substitution. Recommendation systems learned your preferences to suggest products, movies, music, or content you might like. Self-driving cars became feasible, using deep learning to process camera and sensor data, recognize road conditions, identify pedestrians and vehicles, and make driving decisions. While fully autonomous vehicles remain challenging and controversial, the progress from research projects to actual test vehicles on public roads happened remarkably quickly. Game-playing AI systems achieved new milestones. AlphaGo, developed by Google's DeepMind, mastered the ancient game of Go, which has vastly more possible board positions than chess and was considered beyond computer capabilities for years. In 2016, AlphaGo defeated one of the world's top Go players, and in 2017, it beat the world's top-ranked player. The same approach was applied to chess and other games, creating systems that learned to play at superhuman levels through self-play rather than being explicitly programmed. AI systems began creating content. Neural networks trained on paintings could generate new artwork in similar styles. Systems trained on music could compose new pieces. Text generation systems, given a prompt, could write coherent continuations that were often indistinguishable from human-written text. These capabilities raised questions about creativity, authorship, and the nature of art. In 2022 and 2023, generative AI exploded into public consciousness. Systems like DALL-E and Midjourney could create sophisticated images from text descriptions, producing artwork that ranged from photorealistic to stylized, often with quality that seemed professional. ChatGPT, a large language model from OpenAI, could engage in natural conversations, answer questions, write essays, debug code, and perform a remarkable variety of language tasks with apparent understanding and fluency. These systems weren't truly intelligent in the way humans are. They didn't understand meaning in a deep sense, couldn't reason abstractly beyond their training, and made mistakes that revealed their limitations. But they were useful enough and impressive enough to change how millions of people worked, created, and solved problems. Students used them for homework assistance. Programmers used them to write and debug code. Writers used them to overcome creative blocks or generate ideas. Businesses integrated them into customer service, content creation, and data analysis. The rapid advancement of AI capabilities raised profound questions and concerns. Job displacement seemed likely as AI automated tasks previously requiring human intelligence. Writers, artists, programmers, customer service representatives, and many other professions faced potential disruption. The technology seemed to be advancing faster than society's ability to adapt. Bias in AI systems became a major concern. Neural networks learn patterns from their training data, and if that data contains biases, reflecting historical discrimination, cultural assumptions, or unbalanced representation, the AI system will learn and potentially amplify those biases. Facial recognition systems that worked better on some demographics than others, hiring algorithms that discriminated, and language models that generated stereotyped content all demonstrated that AI could perpetuate and scale existing societal problems. The black box nature of deep learning created challenges. Neural networks with millions or billions of parameters are essentially impossible to understand in detail. You can see what they output, but understanding why they made a particular decision is difficult. This lack of interpretability is problematic for applications where accountability matters. Medical diagnosis, criminal justice, financial decisions, autonomous vehicles. Misinformation and manipulation became easier. AI-generated images and videos, sometimes called deepfakes, could convincingly show people saying or doing things they never did. AI-written text could produce propaganda, spam, or misinformation at scale. As these tools became more accessible, distinguishing real from fabricated content became increasingly difficult. Questions about consciousness and sentience arose. Some people interacting with sophisticated language models reported feeling like they were talking to conscious beings. Most AI researchers emphasized that current systems, despite their capabilities, don't have consciousness, don't experience emotions, and don't understand in the way humans do. They're pattern-matching systems, extremely sophisticated ones, but fundamentally different from human intelligence. Yet the subjective experience of interacting with them could feel remarkably human-like. The long-term trajectory of AI remained uncertain and debated. Some researchers predicted that artificial general intelligence, AI systems as flexible and capable as humans across all domains, could arrive within decades. Others argued it remained far in the future or might not be possible at all. Some warned of existential risks if superintelligent AI systems were developed without proper safeguards. Others focused on near-term challenges like bias, job displacement, and misuse. What seems certain is that AI has transformed from a research topic to a practical technology embedded in everyday systems. When you search online, recommendation algorithms powered by machine learning shape what you see. When you use GPS, AI helps optimize routes. When you shop online, AI personalizes your experience. When you take photos, AI enhances them. Much of this AI works invisibly, improving services without users necessarily knowing it's there. The relationship between human and artificial intelligence is evolving. Rather than replacing humans entirely, AI often augments human capabilities. Helping doctors diagnose diseases, assisting lawyers in reviewing documents, enabling scientists to analyze vast data sets, empowering creators with new tools. The most effective applications often combine human judgment and creativity with AI's ability to process information and recognize patterns. It's late at night as we reach the final chapter of our journey through computing's evolution. We've traveled from ancient counting tools to artificial intelligence, from room-sized calculators to pocket supercomputers. But the story isn't over, it's accelerating. The devices in our pockets are more connected, more capable, and more intelligent than ever before, and the trajectory suggests we're heading toward a future where the boundaries between human and machine, between physical and digital, become increasingly blurred. Let's start with quantum computing, one of the most exciting and least understood frontiers. Classical computers, everything we've discussed so far, process information as bits, ones and zeros, on or off. Quantum computers use quantum bits or qubits, which can exist in superposition, effectively being both 1 and 0 simultaneously until measured. This property, along with quantum entanglement, allows quantum computers to perform certain types of calculations exponentially faster than classical computers. Quantum computing isn't better at everything. It won't make your spreadsheet calculate faster, but for specific problems, simulating quantum systems, breaking certain types of encryption, optimizing complex systems, searching vast datasets, quantum computers could provide dramatic advantages. Drug discovery, materials science, financial modeling, and artificial intelligence could all benefit from quantum computing. The challenge is that building quantum computers is extraordinarily difficult. Qubits are fragile, easily disrupted by heat, electromagnetic interference, or even cosmic rays. They must be kept at temperatures near absolute zero. Error rates are high. Scaling from dozens of qubits to the thousands or millions needed for practical applications remains an enormous engineering challenge. Companies like IBM, Google, and specialized startups are making progress. But we're still in the early stages of quantum computing, similar to where classical computing was in the 1950s. Brain-computer interfaces represent another frontier that sounds like science fiction, but is becoming real. These systems create direct communication pathways between brains and external devices. The most advanced current applications help paralyzed individuals control computers or robotic limbs through their thoughts. Sensors detect neural activity, algorithms decode intended movements or commands, and devices respond accordingly. Companies like Neuralink, founded by Elon Musk, are developing implantable brain-computer interfaces with the long-term goal of enabling direct neural connection to computers. The near-term medical applications, helping people with paralysis, blindness, or neurological conditions, are compelling. The longer-term possibilities of cognitive enhancement, direct brain-to-brain communication, or merging human and artificial intelligence raise profound questions about human nature and identity. Less invasive approaches use external sensors to detect brain activity through the skull. While these have lower resolution than implanted electrodes, they're safer and more practical for consumer applications. We might eventually have headsets that let you control devices by thinking, communicate through thought, or enhance memory and cognition through direct neural stimulation. Wearable computing is evolving beyond smartwatches. Smart clothing with embedded sensors could monitor health metrics continuously. Smart glasses could overlay information on your field of vision, providing navigation, translation, information about people you're talking to, or reminders about tasks. These augmented reality interfaces could make computing ambient, always available but unobtrusive, integrated seamlessly into your experience rather than requiring you to pull out a device. The trend toward ambient computing extends beyond wearables. Smart home devices respond to voice commands, adjust lighting and temperature based on your preferences and presence, anticipate your needs. Your car knows your schedule and can suggest departure times for appointments. Your refrigerator tracks inventory and suggests recipes. Computing is embedding itself throughout the physical environment, becoming infrastructure that operates in the background. The Internet of Things, billions of connected devices from appliances to industrial sensors, creates a world where the digital and physical are thoroughly intertwined. Your fitness tracker shares data with your health apps. Your smart lock communicates with your phone to let you in. Your thermostat adjusts based on weather forecasts and your schedule. These interconnections create convenience, but also complexity and vulnerability. More devices mean more potential failure points and security risks. Edge computing represents a shift in how distributed computation works. Instead of sending all data to centralized servers for processing, more computation happens locally on devices themselves or on nearby edge servers. This reduces latency, improves privacy by keeping data local, and reduces bandwidth requirements. Your smartphone processes much of its AI locally rather than sending everything to the cloud. Security cameras analyze video locally to detect motion, rather than streaming everything continuously. The environmental impact of computing is becoming a crucial consideration. Data centers consume enormous amounts of electricity, and while renewable energy is increasingly powering them, the carbon footprint of computation matters. The manufacturing of devices requires rare earth elements and energy-intensive processes. Electronic waste is a growing problem as billions of devices become obsolete. Sustainable computing, designing efficient systems, extending device lifespans, improving recycling, using renewable energy, will be essential as computing continues expanding. Privacy and security challenges intensify as computing becomes more pervasive and intimate. When computers are always watching and listening, when they're monitoring your health and location, when they're embedded in your clothes and potentially in your brain, the potential for surveillance and control increases dramatically. Balancing the benefits of connected, intelligent systems with the need to protect privacy and maintain human autonomy will be one of society's defining challenges. The digital divide could widen or narrow depending on how computing evolves. If advanced technologies remain expensive and concentrated in wealthy regions, inequalities could increase. But if powerful computing becomes cheaper and more accessible, if connectivity reaches underserved areas, if interfaces become more intuitive and language barriers are overcome through real-time translation, then computing could be democratizing. Which path we take involves technical choices, but also policy decisions about access, regulation, and investment. Work is being transformed by computing in ways that are still unfolding. Remote work, enabled by video conferencing and collaborative software, has become normalized in many fields. AI and automation are changing which jobs exist and what skills they require. The gig economy, enabled by platforms that match workers with tasks, has created new forms of employment, but also raised questions about worker protections and stability. Education is adapting to prepare people for careers that increasingly involve partnering with intelligent systems. Human identity and relationships are evolving with computing. Social media has changed how we present ourselves, maintain friendships, and form communities. Dating apps have transformed how people meet partners. Online personas become aspects of identity as real as physical presence. Virtual worlds and metaverse platforms create spaces for socialization, creativity, and commerce that exist purely digitally, but feel genuine to participants. The philosophical questions computing raises are profound. If AI systems can create art, who owns it? If they make decisions that affect human lives, who's responsible? If we enhance human cognition through technology, what does it mean to be human? If we upload human consciousness to computers, is that immortality or something else entirely? These aren't just theoretical questions. They're becoming practical ones we need to answer. What's remarkable about computing's evolution is its accelerating pace. The time between major transformations is shrinking. Decades passed between the first computers and personal computers. Years passed between PCs and the internet. The smartphone revolution took less than a decade. AI capabilities that seemed decades away arrived in years. Quantum computing, brain-computer interfaces, and other emerging technologies might mature faster than we expect. This acceleration creates both opportunities and challenges. Innovation happens faster, solutions emerge more quickly, and problems that seemed intractable become solvable. But adaptation becomes harder, social institutions struggle to keep pace, and the risk of unintended consequences increases. We're developing technologies that could fundamentally transform human civilization while still figuring out how to manage the technologies we already have. The future of computing isn't predetermined. The choices we make as individuals, as societies, as a species will shape how these technologies develop and deploy. We can build systems that empower people or systems that surveil and control them. We can create technologies that bridge divides or deepen them. We can develop AI that augments human potential or that replaces human agency. The technology itself is neutral. Its impact depends on how we choose to use it. What seems certain is that computing will continue becoming more powerful, more integrated into our lives, and more central to human civilization. The transformation from counting tools to thinking machines, from isolated devices to global networks, from room-sized calculators to pocket supercomputers. This has all happened within a single human lifetime. The changes ahead might be even more dramatic. Tonight, we've traced a path through thousands of years of human ingenuity, from the first beads sliding on wires to help merchants calculate, to artificial intelligence that can paint pictures and write poetry. We've watched computers shrink from room-sized machines tended by specialists to devices we carry without thinking, always connected, always ready. We've seen how the desire to calculate evolved into the ability to communicate, to create, to explore ideas that exist only in the digital realm. Thank you for joining me on this journey through the evolution of computers, from ancient abacuses to quantum possibilities. If you're already drifting off, then our mission is complete. But if you're still awake, perhaps another deep dive through one of our previous episodes will carry you gently into slumber. Until we meet again in these quiet hours, may you see the magic in ordinary things around you, appreciate the invisible intelligence woven through your world, and may you rest easy knowing the future is still unwritten, full of possibilities we haven't dreamed yet.